Let's learn an important skill to find the relative mass of gas molecules. We're using Avogadro's hypothesis to find the molecular mass of a gaseous substance. We know that at the same temperature and pressure, equal volumes of gases will contain equal numbers of molecules. That's derived from the law of combining volumes, and it's called Avogadro's hypothesis. Therefore, at the same temperature and pressure, equal volumes of gases contain equal moles. So let's go into the lab and find the mass of gases in an identical container. So these are two containers that are in every way identical, same volume, same temperature, same pressure. In the first, we have 1.50 grams of oxygen. In the second, same volume, same T and P, we have 0.75 grams of methane. If you look at these and we realize that each one of these containers has the same number of molecules, then we can reason that the molecules of oxygen must be twice the mass of the molecules of methane, or in the other way, the methane molecules must be half the mass of the oxygen molecules. So we can write the equation: the mass of the methane is equal to 0.50 times the mass of the oxygen. That's not only true of the whole assembly of molecules, it's also true of each molecule. Each methane molecule is half as large as each oxygen molecule, and we're talking about mass, of course. Now we will assign as our standard oxygen molecule 32 AMUs, and AMU is an atomic mass unit. It's also sometimes called the Dalton. That means that the methane mass must be 32 AMUs, which is the oxygen, times the ratio of methane, the whole assembly of methane, to the whole assembly of oxygen. 0.75 grams of methane over 1.50 grams of oxygen. And that must mean, when we multiply this ratio by 32 AMU, we get 16 AMUs for the methane. So how we set all of these problems up is we find the mass of the oxygen in a container. We find the mass of the unknown molar mass gas in the same container at the same temperature and pressure. So same volume, same temperature, same pressure. And we find the ratio of the unknown molar mass gas mass to the oxygen gas mass. In the case of the methane, that ratio was 0.50. We then multiply that ratio by our standard oxygen mass of 32 grams per mole, or 32 AMUs per molecule, and we get an answer in grams per mole or AMUs per molecule. I like to think of the AMU as being to the molecule as the gram is to the mole. We measure moles in grams, we measure molecule masses in AMUs. So, your turn. In a certain container at 25 degrees Celsius and 100 kPa pressure, there are 2.30 grams of oxygen. We take the same container, flush out the oxygen, and put 4.60 grams of another gas at the same temperature and pressure. What would be the molecular mass of the other gas? Turn this off, try to solve the problem using the formula that I just told you, and then let's check your work. Checking your work, we can see that the molar mass of the gas is equal to the ratio of the mass of the gas to the mass of the oxygen times our standard 32 AMUs per molecule. Well, that's 4.60 grams, that's the mass of the other gas, divided by 2.30 grams of oxygen. So there's your ratio right here. Multiply by 32 AMUs, which is the standard mass of the oxygen molecule, and we get 64 AMUs per molecule. You'll Use the same technique every time. The only complication you might run into is that sometimes the problem will give you the mass of the flask that's containing the gases, and then they'll give you the flask plus the gas mass, and then you'll have to do a subtraction before you do your ratio. But if you do it the way I just told you, you'll get the right answer every single time.